The normal distribution, also known as the Gaussian and also referred to as the bell-shaped curve, is a symmetrical continuous distribution with two input parameters, the mean and the standard deviation. In some cases we need to estimate the input parameters. It's easy to take a guess at what the mean might be, but what's the standard deviation? In this case we can use what's called the range rule. In 2012, Ramirez and Cox published a paper improving the range rule of thumb. And it goes like this, that the standard deviation is the max minus the min divided by 3 times the square root of the natural log of the count minus 1.5. In the chart here, I've used the 3-point method with the inputs of the min, the mean, and the max, and I've estimated the standard deviation using the range rule. And if we look at the descriptive statistics of our 10,000 trials, it shows that the standard deviation is 1. This is the case for the standard normal distribution, which by definition has a mean of 0 and a standard deviation of 1. Excel has two built-in functions for calculating a normal distribution. NormInv, where we input a probability, or which could be just rand, and the mean and the standard deviation. The other function is NormDist, where you put in the x value that was generated by NormInv and the standard deviation, and then you tell it whether you want a cumulative distribution or a density distribution. In this case here, we're doing the density distribution. Another thing to note is that I've modified the range rule by Ramirez and Cox by adding a parameter called the standard deviation multiplier. So what that does is that if I increase this number here, this input, I can expand the standard deviation, and I'll demonstrate this a little bit later on. The unbound nature of the normal distribution is demonstrated here in two ways. One is that with these parameters, and we look at the values that we generated in our table to the left, we see that the min and the max here are beyond the limits that we expressed as the min-max. But this tells you that things can get larger, but I've also included a couple of calculators over here on the right to help demonstrate the unbounded nature of these distributions. Let's take a minute and play with this calculator. Let's say here we're looking at these parameters and this distribution, and let's change the probability here to 0.997, which is about 3 standard deviations. I'll hit Shift F9 and we'll recalculate that, and I see that I get a value of about 2.7, which puts it about here. And notice that with the standard normal distribution, your z-score is equal to your standard deviations. But to kind of show you the unbound nature, I'm going to put in here some ridiculously small probability. Let's say 1 times e to the minus 300. And we'll hit Shift F9, and we'll see that we now have a value that's minus 37, and also the z-score. This is ridiculous. In the second calculator, you just put in a value. Here I've put in 20, and the z-score is about 20, but notice the cumulative probability is 1. After some value, it always becomes 1 and just stays there because Excel cannot resolve the number of digits out beyond the decimal point to calculate this. But we could put in here some ridiculously large number as well. Let's say 1,000. Hit Shift F9, and you'll see here there's our z-score, but this doesn't change. The z-score is a pretty practical parameter to be able to calculate, because in often cases you're going to want to tell somebody that their value is so many standard deviations away from the norm. Let's play around with this normal distribution tool in Excel. So I have another chart here I'll bring up. And let's say that we believe that the mean weight for teenage boys is 100 pounds. And let's say that we think they can be as light as 75 but weigh as much as 125. So those are some symmetrical inputs. And I'm going to hit Shift F9 and recalculate everything. And I get the normal distribution. And notice here that the max goes a little bit more than the maximum input that we put in. And voila, we have this. But let's say I'm a little bit uncertain about that min and max. And let's change the multiplier here. Let's say, we think that, maybe it's 25% more. So let's put in 1.25. And I'll hit return and Shift F9. And you can see that it has broadened. And notice now that the min and the max have also changed here and are beyond the limits of our min-max inputs. So the standard deviation multiplier is useful when you have some uncertainty about what the range of your data is. Let's do one more example. Well, we'll see how the unbound nature can be a problem with the normal distribution. So we'll put in a 1 back to our standard deviation multiplier. Let's put in here a 0.5 and a 1. So in this case here, this might be an example where we're looking at the fraction of sand in a sand and mud mixture, and the values cannot be below 0 and greater than 1, because you cannot have any more than 100% sand or no less than 0% sand. So I'll hit Shift F9, and this case here it worked, and you can see that our min and our max have stayed within the bounds of our calculation. Let's do it again and again, and on the third trial we see that now our min has gotten below our minimum value. So with 10,000 trials, there's the possibility that you will sample beyond the limits of your min and max. And if you have more trials, more than 10,000 trials, the chance that you will sample beyond your min-max values increases. Let's say you have some uncertainty as to what the mean of the data is, or the range of the data. So you may want to again increase this multiplier, and let's make it 1.2. I'll hit return and Shift F9, and now we see that the min and both the min and the max are beyond that limit. And probably every time I run this by hitting Shift 9, with that standard deviation, you're going to be beyond your min-max inputs. Let's do one more trial. In this case here, I'm going to make something asymmetrical. So we'll put our inputs in at 75, 100, and let's make the max 200. Shift F9, and you can see that it will calculate a symmetrical distribution with 100, but really it's nowhere close to what you want your distribution to be. So you really don't want to model asymmetric distributions with a normal distribution. In later videos, we'll discuss some of the tools that are available for modeling the asymmetrical distributions, such as the triangle and beta distributions. So let's set this back to a symmetrical distribution. I'll put in 125, hit return, Shift F9. But I want to deal with these. So what can we do? We can truncate it. And I'll demonstrate that in another video on how to truncate the normal distribution. Or we could use a triangle or beta bound distribution to model Before moving on, I'd just like to point out that what's so great about this normal distribution? Well, one is that it's very common in nature, and it's very useful for doing all kinds of hypothesis testing. And so they refer to this as parametric statistics. There are several techniques for testing the normality of a distribution. There's by visual inspection of the curve that looks symmetrical, and you can look at the descriptive statistics and looking at the mean, the mode, and the p50 or median value, and they should be approximately the same. More robust techniques involve using a quantile-quantile plot, and there are a whole host of normality tests, such as the chi-squared test, which we won't go into in this series. So let's move on to our next video on truncating the normal distribution.